Steve, it is February 7, 2018, and today I'm going to talk about how scientists define three terms, because there seems to be a massive amount of confusion, and sometimes just confusion, sometimes actual misrepresentation of these definitions for one's own purposes, but we're not going to talk about that today. Today what I'm going to do is explain as simply as I can the difference between a scientific fact, a scientific law, and a scientific theory. I am not going to go into how theories develop. I'm saving that for another much longer video. All right, but as most words, words have multiple definitions. All right, and people often are confused. Sorry, the cats are acting up as to what the actual definitions are, or how they apply in science. So I'm going to try to set the record straight here. All right. First of all, a fact. All a fact is, okay, it's a bit of information that has been verified and is not in contention. All right. Some definitions will use the word truth in quotes, but that is the simplest way I can define a fact. A fact is not above a theory. Okay. It is just a piece of information. It can be an observation, it can be a data point, it can be a set of observations, a set of data points. It doesn't matter. Okay? So, like if I go out into the field in geology, I'm chasing a sandstone bed and I get a measurement on it, strike and dip with my compass, which is an objective measuring tool, and say somebody else comes by a while later, takes another strike and dip on the exact same bed and gets the exact same measurement I did. There's a fact right there. That's all a fact is. It's not an assemblage of other facts or stuff, and it's not a proof of anything. Okay? Now, law. I've actually seen people confuse this with the legal definition. I don't even know how that happens. So I'm not even going to address that. But all a law is, and by the way, if I read something, it is from the National Center for Science Education. Okay? I'm going to read their definition to you, and then I'm going to expand on it. All a law is a descriptive generalization of how some aspect of the natural world behaves under stated circumstances. Okay? That is all a law is. It is usually based on facts. A law does not have to be a mathematical expression, although usually in physics it is. But like in geology, the law of superposition simply states that in an undisturbed layer of rocks, or layers of rocks, the oldest one will be on the bottom, the youngest on the top. So if you have a bed here and a bed here, this one is older than this one in an undisturbed sequence of rocks. Okay? So they can just be descriptions like that in simple statements. They don't need to have numerical value. Now, before I get into theory here, I've seen people confuse theorem and theory. A theorem is a mathematical, it has to do with math. All right, we're just going to leave that there. It has nothing to do with scientific theories. All right, it's a mathematical proof. All right, so I'm going to read their definition of theory here, and this is a pretty good one, but they do leave important bits of information out. In science, a theory is a well-substantiated explanation of some aspect of the natural world that can incorporate facts, laws, inferences, and tested hypotheses. I'm not going to get into hypotheses. That's for the video I'm going to do explaining how things develop into theories. Now, that is a very simple definition. I'm going to expand on a couple of things here. Notice how it said can incorporate facts and laws. Facts and laws are just what I explained. They can be within theories. They are not above theories. Okay? A theory is as good as it gets in science. We do not prove anything beyond a shadow of a doubt in science. Shadow of a doubt is a legal term. It has nothing to do with science. Just like insanity. I mean, we all have a definition of that, but insanity appears in law, but I don't know of any psychologists that have ever clinically diagnosed someone insane. All right? Could be wrong on that, but I'm pretty sure they haven't. So, notice these things are within a theory, and they can transcend theories because ultimately, everything we do in science is subject to the laws of physics. Everything goes back to physics, ultimately, okay? And in here they do touch on the part, well-substantiated explanation. What does that mean? Well, an important part of a theory, okay, is its ability to make accurate predictions, all right? And it needs to provide mechanisms for how those predictions can either be verified or, to assert those predictions, or mechanisms explaining the data presented. And it needs to be inherently falsifiable. That being said, if you can falsify a mechanism within a theory, that doesn't negate the theory as a whole. That falsifies the mechanism, and that happens a lot in science, all right? When we develop these theories, we may not have a substantial body of knowledge to provide any reliable mechanisms. But as time goes on, and the theories, new mechanisms come about and whatever, the old ones are dropped and the theory gets better and better and better. Now, what else did I tell you? My train of thought just derailed. I did covered mechanisms. Oh yes, predictability. If a theory cannot make accurate predictions, it's not a very good theory. Okay? And it wouldn't be accepted within the scientific community anyway, because you need to be able to predict things. And theories in the past have been falsified. Like take geology, for example. Neptunism was falsified back in the 19th century, okay? Because it was an okay idea at the time and seemed logical, but then the mountain of evidence just blew it out of the water. Bad pun. All right, but something more recent in geology would be continental drift versus plate tectonics. Plate tectonics did not supersede continental drift as a theory. The two are separate. Continental drift by Alfred Wegener didn't explain much of anything. He did not have a theory. He had an idea. He had a hypothesis. And he didn't really provide any mechanism. His basic premise was the continents move about the globe. Okay? And that's a basic part of plate tectonics, but that's where it ended for him. And he also thought the ocean basin was flat and featureless and the continents moved on top of those. But he didn't provide any mechanisms. So he didn't have a theory. Plate tectonics takes that a lot further. We can observe, like the North American plate moving relative to the Pacific plate in spots, as an example, and that becomes observations that we use to build the theory of plate tectonics. We see things like mid-ocean ridges, subduction, deep trenches, the Ring of Fire. All this stuff is incorporated into that theory. What drives these plates is still a matter of a little bit of debate in the scientific community. But plate tectonics replaced the entire idea of continental drift. All right. So I hope that kind of clears things up a little bit. But if you want me to extrapolate or have any questions or need me to clarify anything, please leave a comment below. I will entertain any actual realistic questions. Please, I hate to do this, but please subscribe. I'm trying to beat that deadline just like the rest of us small content creators. But anyway, that is it, and I hope you learned something.